let's continue estimating with the linear approximation method. So find the linear approximation of f of x equals x sine pi x squared about x equals 2. Use the approximation to estimate 1.99. As soon as you see a question like that, you should be thinking the linear or tangent line approximation. We're already given our nice value of x, the x naught, right? It tells us about x equals 2. We're already given our function, f of x equals x sine pi x squared. Right, so change in x, right, is going to be, so we're using 2 to approximate 1.99. Right, our value is a little less, right, so our value is less, so we're expecting something smaller, so this should be negative, so 0.01, negative 0.01. Right, so now let's find the derivative, and we're going to need to use the product rule. Right, so u is x, and v is sine pi x squared. All right, and that's going to be a chain rule in that part. Du is pretty easy. The derivative of x is 1. Derivative of sine pi x squared, right, so dv is going to be the derivative of sine, which is cosine blop, times the derivative of the pi x squared. So that's going to be, so derivative of pi x squared is going to be, using the power rule, will be 2 pi x. So dv is going to be 2 pi x cosine pi x squared. All right, so there we have our derivative. And so now using the product rule, it'll be the first, x, times the derivative of the second, so times 2 pi x cosine pi x squared, and then plus the derivative of the first, which is just 1, times the second. I'm going to have to move this down just a little bit. And the second is sine pi x squared. All right, so we could simplify that a little bit. So we could combine the x and the 2 pi x. That would be 2 pi x squared cosine pi x squared plus sine pi x squared. There we go. All right, so now we need to evaluate our derivative, right? So, and evaluate our function. So f prime of 2 is what we're using. All right, so that's going to be 2 pi times 2 squared. Excuse me. Times cosine pi 2 squared plus sine pi 2 squared. Right? So that's equal to, right? So we've got 4 times 2, that's going to be 8 pi. And then cosine 4 pi plus sine 4 pi. Well, cosine and sine 4 pi is the same as cosine and sine 2 pi is the same as cosine 0 and sine 0. Right? You're just going around the circle. Right? So cosine 0, sine 0, you haven't gone around the circle. Cosine 2 pi, sine 2 pi, you've gone around the circle once. Cosine 4 pi, sine 4 pi, you've gone around the circle twice. Right? But either way, cosine 0, 2 pi, 4 pi is going to be 1. So this is 8 pi times 1. And sine 0, 2 pi, 4 pi is 0. So this is 8 pi. All right, so that's the value of our derivative at 2. All right, and let's find f of 2. Although we could also find it up there. But since this is such a long equation, maybe it would be a good idea to just find it up here first. All right, so f of 2 would be 2 sine pi 2 squared and that's going to be 2 sine 4 pi, which is 2 times 0, or 0. I will write it again as part of the linear approximation method, just showing you, okay, that's where that value came from. Right, so, but we have it down there as well. So we are approximating 1.99. I think I wrote really big. So that's going to be what we get when we evaluate 2, right? So that this first part was just 2 sine pi 2 squared, and then plus the value we got for the derivative, which was 8 pi, times the change in x, which I'm going to leave it. Oh, let's change that to a fraction because it's easier for me to deal with. All right, so that's a negative 1/100th. All right, so that is going to be, we know this was 0, and this is now going to be minus 8 pi over 100, and we could reduce that. Right, they're both divisible by 4, so that's going to be negative pi 25ths. Right, and that would be the approximate value of 1.99. Right, if it got to 2, right, then it's going to be positive. If it's only at 1.99, it's going to be in the fourth quadrant. It's going to be negative. All right, so there we go. Another one done. Now, this is really, really easy, and it's a slightly different formula. It's linear approximation for roots or powers near 0. Right? And it has to always follow the same thing. Right? So it's going to be where you've got something that's near 0. Right? And so we're doing approximation for a value near 0. So your x naught is going to be 0. Right? And you have got something raised to a power. It could be a fractional exponent. It could be it could just be an exponent. Doesn't matter. Right? It could be negative exponent. So here is the model. So f of x equals, so if you've got 1 plus cx to the k power, where you're really close to 0, it is always going to be 1 plus k times c times x. C and k are constants. Right? X is the only variable. Right? And that x is going to get replaced by some value. Right? So here we want x, in this particular problem, we want x to be 0.001. So that's really close to 0. So we can use this formula if we have a function raised to a power. Right? So it's just kind of an easier way to deal with a function that's raised to a power. So given f of x equals 1 minus 2x to the 3 halves, find L of x near x equals 0. And here at x, the x that was going to be near 0 is going to be 0.001. If we don't know what x is, all we can do is write the equation that we would use, but we couldn't actually evaluate. Here we're going to be given that x is going to be 0.001. All right, so now in that formula, k and c are constants. K is the exponent. All right, so k is 3 halves. C is the coefficient. The coefficient, and it's the coefficient on x. So the coefficient on x is a negative 2. All right, so that means that our value is going to be approximately 1 plus, and then k is 3 halves, times c, which is negative 2, times x. So that gives us 1 minus 3x. All right, now we could use that function to evaluate any value near 0. So we want to know, okay, well, what if x is 0.001? Then what would it be? All right, so we plug in 0.001 into our equation, and we get 1 minus 3 times 0.001, or 1 minus 0.003, or 0.997. The actual value, if we evaluate this in a calculator, is 0.9970015,005. So you see, we're accurate essentially to the 6th decimal place. That's where we have an extra value, because we can put 00 after the 0.997. So this is very accurate for roots or powers near 0. and it always follows the same format. There's a few little interesting things, all right? If you're, so here, x didn't have an exponent. If x has an exponent, it just gets included with c, all right? So here we're using our model, f of x equals 1 plus c of x to the k power. If that's what our function is like, we can approximate this using the equation 1 plus kcx, where k is the exponent and c is the coefficient. Right? And if your coefficient, if you have your x has an exponent, include that along with it. So now we don't just have the 5. If that was 5x, we just have 5. But since it's 5x to the 4th, we're going to have 5x to the 4th. All right, so first of all, I rewrote that because that's not really an exponent, is it? But a cube root can be rewritten as an exponent. So f of x equals 1 plus 5x to the 4th to the 1/3 power. All right, so our k is the exponent, 1/3. Right? Not the exponent on x, but the exponent on the whole expression. C is, and it's only when we have 1 plus something. C is the coefficient, but since x has an exponent, we're going to include that exponent, and so c is going to be 5x to the 4th. So now a function to evaluate for any power near 0 would be 1 plus k, which is 1/3, times c, which is 5x to the 4th. Now we don't have another x, because we already got the x included. And that would be 1 plus 5/3 x to the 4th. So that would be the function that we would use to evaluate any value near 0. We're going to evaluate when x is 0.001. So now we'll plug that in. So we've got 1 plus 5/3 times 0.001 to the 4th power, which I have right there. It's pretty easy to raise one with zeros to any power every time you just add more zeros. So our final answer is going to be 1 point, a lot of zeros there, 1667. And it is very close to the actual answer. So this is for evaluating for powers near 0. All right, so x is pretty close to 0 because x is 0.001. Right, and so it doesn't add very much. It only added 0.0000000001667, having that little extra added to 1, because x was really close to 0. All right, so this one I don't have everything is written out as much. All right, so these are so easy and formulaic. I think I even have them written out in your notes. All right, so f of x equals 1 plus cx to the k power is approximately 1 plus k times c times x. Notice that looks a lot like the power rule, by the way. All right, so not quite, but a lot like the power rule. And that's mainly because we've got a 1, which isn't going to make any difference. Right? We're going to be including that 1. All right, so we have 1 over 1 minus x. We could rewrite that so that we have 1 plus something raised to a power. All right, so rewritten, this would be, and let me just write f of x equals. This would be 1 minus x to the negative 1 power. All right, so your k is negative 1. That's the exponent. Your c is the coefficient on x. It's negative 1. Right, so this would be 1 plus, right, we would have k times c times x. So that's going to be 1 plus x. Right, so it's pretty easy to evaluate. If x is 0.001, what would the value of the function be? We would have 1.001. Right? So this is just a related use for roots and powers near 0 of the linear approximation method. All right, so again, we want to rewrite this one. So we have f of x, probably just put f of x here, equals 1 over the square root of 1 minus x squared. That's the same as 1 minus x squared to the negative 1/2 power. All right, so k is the exponent. That'd be negative 1/2. Here we've got an exponent on our x, so include the exponent with x. So our c, or cx, is negative x squared. So we're going to have our value of our function for values close to 0 will be 1 plus k, which is negative 1/2, times c and the x together, negative x squared. So that'll be 1 plus x squared divided by 2. Right? So that means if we want to find out the value, if x is 0.001, what's the value of the function? We can use that formula, and that would be 1 plus 0.001 squared divided by 2. That would be 1.00000005. Right? So we can evaluate for values really close to 0. I think that was the last one. This is the last problem I'm going to do. Estimate the value of the function given x naught. Right? So find f of x and use the value to evaluate f of x naught. I already wrote that in there. So f of x is e to the x. I don't know what e to the negative 0.1 is, but that's pretty close to 0. Right? And I do know what e to the 0 is. So x naught will be 0. The change in x will be negative 0.1 minus 0, so negative 0.1 or negative 1/10. Let's write it as negative 1/10. All right, let's take the derivative. That's pretty easy. F of x is e to the x. F prime of x is e to the x. It is its own derivative. Calculate the f prime of 0 would be e to the 0, and that is 1. That's pretty easy. And then substitute into the tangent line approximation to find the equation of the tangent line. So we are finding the value, right, using the tangent line, because values that are very close to the point of tangency are going to be, so values that are close to x are going to be really close to the value we get from the tangent line. And the line is always easier to work with. So L of negative 0.1 is equal to e to the 0, our nice value, plus the value we got for the derivative, which was 1, times the change in x, which is negative 1/10. Right? So e to the 0 is 1. So we've got 1 minus 1/10. So that's going to be 9/10. I'll just put it here. So that is the approximate value of e to the negative 0.1. Right? And we expected it would be a little less than 1, right? Because e to the 0, which is a little more than 0.1, negative 0.1, was equal to 1. Right? So that's the last one I'm going to do on this video. Thanks for watching, and bye for now.